let's have a look at what it means for a linear transformation to be onto. So onto, a linear transformation is called onto, or surjective, that's sort of the fancy word for it, if for every vector in the target space W, there's some vector in the domain space V that gets mapped to W. Right, so this is just the technical way of saying that every vector in W gets hit by something from V. So to work with onto transformations, it's actually kind of convenient to know a property of linear transformations that is actually true for any linear transformation. This doesn't really have anything to do with onto transformations in particular. So it turns out that if we have a linear transformation, if the images of some vectors are linearly independent, then the vectors you started with had to have been linearly independent to begin with. So let's show that this is true. How can we show that these vectors are linearly dependent or independent? Well, let's suppose that we have a linear dependence relationship. So suppose a1 v1 plus dot 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 up to ak vk add up to 0. Okay. Well, what we can do is hit both sides of this equation with t. On the right-hand side, t of 0 has to be 0. On the left-hand side, we can use the linear transformation property of t. We get a1 t of v1 plus dot 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 down to a k t of vk. But remember, we were assuming that t of v1 up through t of vk are linearly independent. So t of v1 through t of vk are linearly independent. And here we have a linear dependence relationship among them, but that must mean that this is the trivial linear dependence relationship. So a1 is equal to 0 and so on down to ak equal to 0. So taking a step back, we assumed that we had a linear combination of these vectors equal to 0. We showed it had to be the trivial linear combination. So that means that the v1 through vk are linearly dependent. Okay. So if a transformation sends vectors to a linearly independent set, the vectors had to have been linearly independent to begin with. All right. So we have this definition of onto, right? This idea that an onto transformation is one where every vector in the target space, W, actually gets hit. Let's look at an example of this just to check that we understand how this definition works. So here's a linear transformation. It's a transformation from R3 to R3 represented by this matrix. Is it onto? Well, let's see. How could we solve this question? Remember, onto is saying that for every possible vector we could put on the right-hand side, there's some vector that would produce W as its output. But T is multiplication by A, so what we're really saying here is A times V equals W always has a solution. Okay, but when does this sort of equation always have a solution, right? Imagine solving this. How do you solve this sort of equation? You row reduce it, right? You row reduce A and see what the reduced row echelon form looks like, and then you sort of put, I guess what we would need to do is augment A with W, and then row reduce. Right? But what would the row reduced form have to look like? The thing is, since we want to know if this equation always has a solution, so this vector W could be anything, and really is anything, because we want to solve this equation for every W to see if there's always a solution. So after you do the row operations, anything at all could show up in this augmented column. So anything could show up here. So what would have to be true about the reduced row echelon form for this to always have a solution? Well, remember, what causes there not to be a solution is if we have something non-zero in our augmented column, but a row of zeros in the matrix portion of this augmented matrix. So for this equation to always have a solution, that means there can't be any rows of zeros. In our reduced row echelon form. Okay, so what we figured out is this equation always has a solution if and only if there are no rows of zeros in the reduced row echelon form. Okay, so all we need to do is reduce this matrix and see if there are any rows without zeros. So let's see, I guess maybe, so I won't drag you through row reducing this whole monster, but what you get is, I don't remember what shows up here and here, but it turns out the last row is 0, right? So there's a row of all zeros, so the linear transformation that this matrix represents is not 1-to-1, right? Because after doing this row reduction, I don't remember what goes here and here, right? We're asking, is it possible that this equation always has a solution? Well, no, not always, because if I put a 1 in this last entry, it's impossible to choose a vector xyz so that this product on the left has a 1 in its last entry. So you can see how it's the row of zeros that makes this equation have no solutions for some possible choice of vector on the right-hand side. So is it onto? No, it's not. Okay, and the reason is because this equation always has a solution if and only if no rows of zeros in the reduced echelon form. Well, actually, this property, the fact that this property is equivalent to being onto is just one of several properties that's equivalent to being onto. So let's look at some of them. So it turns out these are all equivalent. So suppose T is onto, what would its rank have to be? Well, we just showed T is onto if its matrix A has no rows of all zeros, but if it has no rows of all zeros, and right, it's going from Rn to Rm, what is the rank of A? Well, if there's no rows of all zeros, then that means that there's a pivot in every column, or sorry, pivot in every row. There doesn't have to be a pivot in every column, actually, but there's a pivot in every row. But if there are m rows, then that means that the rank of A is m. Right? And all of these things are if and only if statements, so they go forwards and backwards, so that means these two are equivalent. All right, so really it's this last one that's tricky. So turns out that T is onto if and only if T has a right inverse. So what is a right inverse? Well, a right inverse is a function that when you compose it on the right, you get whatever the appropriate identity function is. In this case, I guess it's going to be R, the identity on Rm. Okay, so let's suppose T is onto let's find a right inverse for T. Let's let W1 up through Wm be a basis for Rm. It could be the standard basis, but actually it could be any basis at all. Now, because T is onto, each of these W's gets hit by something coming from Rn. So let's let V1 up through Vm be such that T of V1 is W1, and T all the way up to T of Vm is Wm. All right. Now we can define a linear transformation from Rm to Rn by, let's just say that S of W1 has to be V1 all the way down to S of Wm has to be Vm. Okay, so now we have a candidate for a right inverse. Let's check that it actually is a right inverse. So let's check that T composed with S of some vector is just that vector. And V has to be in Rm here, right? Since S is hitting it first, V has to be in the domain of S, which is Rm. And you know what? Maybe it would be better to call it W instead of V. So let's do that. Okay, so we have this vector W. We need to see what happens to it when we hit it with T composed with S. Well, W, since W is in Rm, we have a basis for Rm. So we can write W in terms of that basis. So let's write W is some linear combination of all of our W's. So A1 W1 plus dot 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 down to AM Wm. And then let's see what happens when we do T of S of W. Right, we're hoping that this is equal to W. So let's calculate. Well, W is A1 W1 up through, plus dot 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 down to AM Wm. But we can use the linear transformation property of S to write this as T of A1 S of W1 plus dot 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 down to AM S of Wm. Okay, but what is S of W1? Well, it's V1 just by definition plus dot 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 down to AM S of Wm, but again, that's Vm. But now we can use the linear transformation property of T. So this is this is A1 T of V1 plus dot 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 down to AM T of Vm. But, so what is T applied to V1 through Vm? Well, remember, how we came up with the V's was by using the onto-ness of T to solve these equations, or to come up with solutions to these equations. So T of V1 is actually just W1. So this is A1 W1. But the same thing goes for all the other W's, so this is down to AM Wm. But this linear combination of the W's is exactly W. Right, so we found that T of S of W is just W, and that means that S is a right inverse for T. Also, it means the matrix of S is a right inverse for the matrix of T. All right, so we showed that 1 implies 3. Now let's do it the other way around. Let's suppose we have a right inverse. Let's show that T is onto. Okay, so let's suppose that S from Rm to Rn, this is an M here, is a right inverse for T. In other words, right, what that means is that T composed with S applied to any vector W is W. Okay. we need to show that T is onto. Right? We need to show that T hits everything in Rm. So let's take W in Rm. We need to find something in Rn that hits W. So let's let, right, what possibly could it be? How could we find something in Rn when we start with W in Rm? Well, there's only one candidate for how to find something in Rn when we're in Rm, and that's use S. So let's let V be S applied to W. Right? It seems like this is a good candidate. So let's calculate what T does to V. Well, T of V is T of S of W, but S is a right inverse for T. T of S of W is just W. So for any vector in Rm, we found a vector in Rn that T sends to W. And that means that T is onto. So that completes the last thing to show here, that 3 implies 1. So all of these three conditions are equivalent.